Hi everybody, welcome to week 5, lecture 2, and today we're going to look at a topic called pointers. Okay, so as usual, you can access the code that we're doing and let me know in the chat if there's something you can't access if you notice it while the lecture's going. And yeah, and people moderating the chat, let me know as well if I missed that. Okay. Next week is Flex Week, and that's like for all of your courses, but there'll be no lectures or tutorials or labs next week for this course. So we're not going to give you any more new material next week or, give you any more work to do, but you've still got your assignment 1 to work on and your lab 5 to do. So we are running help sessions and revision sessions. So yeah, next week is a really great chance to get on top of all your coursework, get some, good sleep into hopefully as well. All right. Now for the revision sessions, like I said, there will be revision sessions next week. They're going to be online only because, not everyone's in at campus next week. The details will be coming out soon. So look out for the forum posts and emails because you'll have to register, and you can also vote for, the topic you're most interested in covering in the revision session. So yeah, keep your eyes out for that. And as always, check out the help sessions. Don't leave it to the last minute to get help. All right. So last lecture, yesterday, we did a strings recap. We did arrays of strings and command line arguments as well. And we did a larger array program, Mud and Bones, to help people get started with assignment 1. I didn't quite finish all the code I was going to do for that. If anyone is really keen to see the rest, just let me know. I can either release the code or just do a quick video, 5 minutes finishing the code off. All right. So in today's lecture, I'm just going to do one more string functions example using a function called struct. So we didn't look at that one before. Let's have a quick look today. And then we're going to start pointers. And while we do pointers, we're going to talk more about memory and the stack. And we'll probably do a Kahoot today that includes 2D arrays, strings, a little bit about command line arguments as well. We'll see how we go. All right, let's get started. I don't know why I wrote hello world word struct. Okay, it should be, anyway, let's see what it is. I'll fix that later. It's hello world struct. Okay, so there's a function in the string.h library. We haven't looked at it yet. There's lots of functions in the struct library, but I just want to do another example of strings because it does take a while for people to get used to strings. Okay. Right, here's my pen. Good. Yes, so with struct, it concatenates 2 strings together. So concatenate just means join. So in this example, and this is just an example I've already done, we'll have another look at an example that we'll do together. I've created a string of max length 20. I never draw these things big enough. Hang on. But anyway, in this string, I've got, let me just move that over there. I've got HELLO, and it would have null terminator in there, right? And then the rest of this array up to index 19, I haven't counted it exactly. It's going to have capacity for more letters. All right. And what we're doing here is we're trying to join together what's in this string already. So we've got this message array and we're trying to add the string world onto the end of it. So what struct will do is it'll just join these two things together. So we'll have hello. It's not going to put a space in there for us unless we tell it to. It'll have hello world, and then it puts the null terminator at the end. Okay, so if we do something like this, oops, and we run it, it should print out hello world, but there's no space between it. We didn't put a space between it. If we wanted to, we could. So that's all strcat does. Now the important thing though is that this string is big enough. So if we do something like this, oops, let me do this again. If we do something like this, this is what our message array will look like. What's going to happen if we use strcat now, do we think? So I've got my message array here. I try and do this strcat. What's going to happen? Yeah, and strcat will make sure it's got the null terminator at the end. Strcat just joins two strings together. Yeah, so what it does is it tries to copy on. So I've got this string called message. This is message here. And it's trying to add on to whatever's in this string already. It goes to this null character at the end, null terminator, and it starts trying to basically copy over the other string here. So it'll try WORLD null terminator. What's the problem in this case? There's no room for this. So when you use strcat, it's just going to join the two strings together and put the second one at the end of the first string. But in this case, there's no room for it. So just a reminder, just be very careful of the size of all your arrays when you're working with strings. Let's try it. So this is going to crash. Because this array that we're trying to add world to the end of, it's just not big enough. If we go back to how I had it originally, where there was, well, not plenty of space, but there was enough space for all of this to fit, it did work. Okay, so the point I'm making here is one, there's a function called strcat that can join strings together, and two, just be very careful that there's enough room in your strings before you're copying things into them or joining them together, etc. Okay, does that make sense? Now, if you did strcat hello world, let me just go to here. If you did something like this and you just typed hard-coded hello world in, this is not going to work either. Right, we haven't even stored this properly in a proper variable, and there'd be no room in there anyway. This would also crash it. Okay, so you have to make sure you're joining together something that's living in an array and the array has enough space in it to fit the next part that it's copying in. Hopefully that kind of makes sense. All right, so that's strcat. Now, having said that, let's see how we might use it. So in this example, yeah, you can join it with two arrays. And in this example, that's what I'll do. Again, though, you've got to make sure that the string you're copying in or the array you're copying from, you know, you're not going to go over the bounds of the new one. So here, what I'm trying to do is, you know, someone might enter their name. Oops. As two separate strings. Sorry, let me do it like this. I'm going to use fgets. We're going to enter a first name and a last name. And then in full name, I want to join these strings together, but like we sometimes see things, you know, with the last name first, a comma, space, we want to format it like this. So the user, let's just see what I've done so far. I've got an array for the first name and an array for the last name. And it's saying I'm not using that variable. That's true because we haven't finished. And if I say Tina, arena, it reads that in. And I've also done this. So remember, I'll just get rid of it for now. When I use fgets, I'm probably going to have a new line in there. So we did this yesterday, actually. I'll leave it in there. So I've got a call to a function to get rid of the trailing new line we get when we enter our data with fgets. All right, so right now, I've got 3 arrays. I've got first name, and it's of length about 200, okay? And I've got, you know, some string in there. I've got a second array that has another string in there that's the last name. And what I'm trying to do is join it together so that in full name, I've actually got, you know, let me write it, arena, space, was it space, comma? Comma, space. Tina. Okay. All right, yeah, I want to remove the new line first. So I'll get rid of it. I'll get rid of doing this first. Now, what do you think we should try and do first to solve this problem? I'm going to try and create this last name variable. What's the first step? So right now, what's in our full name variable? What's in our full name variable at the moment? Well, it's very big size. I made sure it's plenty big enough, even if the person who types in their name has a very long name and it fills up, you know, those other 2 arrays, this is going to be big enough. But right now, what's in there? Nothing. It's just uninitialized. Okay. So if I somehow want to create this array and sort of get all that data in, the arena, a comma, space, and Tina, what do we think the first step might be? Do we want to do a string cat? Yeah, the first step should be copying something into this array, because right now, this array is not actually a string. This is just an empty array. There's no null terminator or anything in there. So the first step is, let's just copy at least the last name in. Okay, and I'll do it up here. Let's do string copy, and into this full name array, let's just copy the first name that the user typed in. And then let's print it out and see what we get. Oh, I didn't want first name, I wanted last name. What am I doing? So far in this array, I've got my full name array. I've copied in the last name, but we can see we've got this extra new line because we read it in with fgets. So that's what we've got in here. So yesterday we saw how to write a function to remove those trailing new lines. So I'm going to make sure that I use that to get rid of the new lines that we get when we read in with fgets. So you can go and watch yesterday's if you didn't see that. So I'm going to write, oh well. Okay, so now we've got arena with no new line in there, which is good. All right, what do we want in there next? We wanted a space, a comma, then a space. So how can we add a comma and a space to the end of this string? Yeah, go and claim chocolates in real life if you think you deserve some. How do we get the comma and the string into the full name now at the end? Well, basically, if we're adding a string to the end of another string and there's room, we can use string cat. So we could say space, comma. Now, someone's making a very good point that generally speaking, we should do string lengths of full name, string length of the string we want to concatenate together, and make sure there's enough room in the whole string. This one, I've concocted it in a way where I know the max length of the first name and the last name, and that's kind of gives us an idea of the maximum that this whole full name could be. But yeah, generally speaking, that would be a very good idea. Okay, then at the end of that, so what I've done now is I've put string cat will have put a space, a comma, then a space. I'll just put it like that in there. Then again, we want to join on another piece of this. So we're going to put string cat, like this. So when we put that all together, we've copied in the last name, we've concatenated on, I keep doing the comma and the space wrong. I don't know why. Space, then comma, then we concatenate on the first name. And I made sure my array was big enough that no matter what, in this case, it'd all fit in. So let's try it. Ta-da! All right, so that's just a reminder of strings, and it's just string cat. Is everyone clear what string cat does? Someone's imagining a string and a cat. Oh, I know. Actually, we had an assignment in 1521 with cats rolling balls of string. Anyway, we didn't need to use string cat to do it though. Okay, so that was just a bit of a recap. Let's go and move on. And we're doing something called pointers. Now, pointers, I think like most of the topics we teach you, when you first hear it for the first time, yeah, it's tough and it's challenging to get your head around. But like everything, the more you use it, the more you think about it, you know, the more you get used to it. Okay. All right. So before we can talk about pointers, we have to talk a little bit about memory and addresses. So this is sort of stuff we've spoken about before, but in more detail. So when we say the word memory in this course, we're talking about RAM, the place that sort of short-term memory that stores data about your program as it's running. And that memory, I'm just going to call it memory from now on, is just like a big array of bytes where you can store data. And the memory addresses are kind of like the indexes to these bytes. So every byte that we store in this memory has its own address, right? And an address, it's just like you've got an address where you live kind of thing. Web pages have addresses or URLs. It's just, yeah, an address where the data lives, and every single byte in that has its own address. Now, typically, when we're printing out addresses or talking about addresses, often we tend to write them in hexadecimal. So if you ever see a number in C that has this 0x, the 0x isn't really part of the number. That's just a prefix saying this number is in hexadecimal. And even if you don't see that, if you see a number that has letters in it, you can probably guess it's hexadecimal. So you don't have to be a master of hexadecimal to understand this, but you know, when we're counting in decimal, which is base 10, we've got 10 digits. And once we get up to 9, there's no more digits. We start combining digits. When we're in hexadecimal, that's base 16. So when we're counting in hexadecimal, we use all the normal digits. Oops, did I just leave out 8? Oh my goodness. If we can count, we use all the digits up to from 0 to 9. But in hexadecimal, we've still got more digits and we start using A, B, C, D, E, F. So in hexadecimal, A is 10, B is 11, C is 12, etc. And it's not until we get up to F where we then start combining digits. So if we did 10 in hexadecimal, that'd be 16. Anyway, don't worry about converting things. Just realize when you see things like this, they're just hexadecimal numbers. And, you know, we often represent our addresses in hexadecimal. All right. Now, in my slides, just a quick disclaimer, I'm often drawing in fake addresses that I've made up. They're not realistic. Usually our addresses have a lot more digits in them, the real ones. Does anybody know? Oh, I think I've got it on the slide. So our system is a 64-bit system, which means our addresses are all 64 bits, which is 8 bytes. So our addresses are all 8 bytes long and yeah, have lots of digits and go up much higher than my fake ones here. All right, so let's just talk about C and what's happening in some simple programs. So when I declare a variable, which is saying the int x part, I'm asking for a chunk of this memory and I'm asking for 4 bytes because it's an int, at least on our system. And basically the system will give us a chunk of memory and we get to call it x. We get to call it x instead of having to know this actual address. That's probably different every single time we run our program. And anytime we refer to x in our program, this particular x, the system knows to go to this particular address. So when we declare it, we get the chunk of memory, and now we're assigning 1 and we're putting 1 into this address. We're setting the byte at this address to be 1. And typically we don't need to know what that address is because we just call it x in our program. But behind the scenes, that x value will have a starting address where the first byte of that will live. Now, and you know, when we do x++, C knows the address where x is, it goes to it and it increments it. So, you know, the values in here changes, but it's still stored at the same location or the same address. Is everyone happy with that? Yeah, every variable will have an address. And we are lucky we just get to use the name that we've made up to, you know, instead of having to work directly with these addresses most of the time. Now, sometimes we actually want to know the address of things. And there is, I mean, a lot of the time we don't, but sometimes we want to know the address of our variable. And to do that, we use this operator. And this is the address of operator. And you've seen this before, but if I say what's the value of x, well, the value of x is 2, But if I say what's the address of X and put that ampersand in, it's going to go and give me the address where this variable lives. So in my fake scenario, that would be the address. If we went and ran it, you know, it'd be some realistic address. And %p is the thing we use in printf if we want to print out addresses. Now, normally we don't really go around printing addresses unless we're trying to debug things or learn things or understand things. Usually the specific addresses don't matter. It's the concept of what's going on. So where have you seen this before? Putting ampersand X or ampersand something. You've all done it and typed it in. Yeah, in scanf. Yeah. And we've said before, we won't tell you why you have to do it, just do it. But what you're doing is you're passing in the address to scanf. So when you're printing something with printf, you don't have to do it. You're saying, here, go and print the value of 2, or whatever you're saying. You just pass in the value that's in the variable. But when you're doing scanf, there's no use passing in the value. You need to pass the address so scanf can go to that address and fill it with your data. So yeah, when we do this, we're saying scanf, here's the address of Y. When you read the data in, the integer that the user types in, go to that address and put the data in there. Just say the user typed in 99. So that's what we've been doing. So it's a bit like, you know, in Uber Eats, I have to put my address in so they can come and deliver my pizza or whatever. Here, scanf has to, you know, deliver that number to that particular address. So that's why we've been doing it. So that's one use for this thing, and we'll see other uses, or similar uses really. But that's all it is, it's an address. But, you know, sometimes we might want to store an address in a variable. We might want to store an address of something to use later for whatever reason. And we do that in life as well. We store addresses of people. I mean, back when I was little, I had an address book that I wrote people's addresses in pen. Is that just because I'm old? Did anyone else do that? Or you might have, you know, contact list in your phone or something. We store addresses so we can look them up and go to that location later. Okay, so yeah, there is a way to store addresses in variables in C, because sometimes we want that address so we can use it for whatever reason. Just like scanf wants that address, so it could go put the data in there. Sometimes we want a variable that can store an address. That's all a pointer is. A pointer is just a variable that can store an address. When you declare it, you have to say what sort of type of address it is. So here I've got a variable called number PTR. I'm just going to call that number pointer. Again, these are variables. They could be called anything and hopefully something meaningful. And this star here means it's a pointer. So if you didn't have that star here, it'd just be a regular int. When you've got that star here, it's saying, oh, okay, this is a pointer, which means it can store an address, and it can store an address, in this case, of an integer variable or an integer. So you have to be specific about the type. So if you've got an integer pointer, it should only be storing addresses of integers. If you've got a double pointer, it should only be storing addresses of doubles, etc. But you can have a pointer to basically any type, but you've got to specify what that address is for when you declare it. Okay, so that's a pointer. It's a variable that can hold an address. Any questions? It's not similar to structs. It's like basically, I'll show you some examples. It's just somewhere where you can store an address. Yeah, what's the point? Well, I'll show you the point soon. The point. Anyway, I'll show you the point soon, but just think of scanf and the ability of a function like scanf to be able to go and modify our variables. So we'll get there, but for now, let's just see how these work. Yeah, and I'll show you printing them out soon. It's going to give some, long number like that. That's correct. All right. So in this example, I've got x is equal to 2. Let's draw it here. X, this isn't a good way to do it. X is equal to 2. Down here, I've got something called x pointer. It's just a variable too, right, as well. We're initializing this to have the address of x. Now, I don't really know the address of x, but let's pretend x is living at address F3, which isn't realistic, but let's just say it is. Well, basically, this variable stores that address. That's it. It's like, what's your address x? And it's noting it down or storing it for later. But we call it a pointer because it's as though this variable points to here. Like if you wanted to find out where x lives, this pointer can point you to it. It knows, right? So this is all a pointer is. This is storing the address of this, in this case, this variable. And that's fine because this is an integer and this is an integer pointer. So over here, if I've got a double, I've got y has, the value 1.5 in there. I've got this variable that's a double pointer, or a real pointer, I should say, and I'm making that point to y. Okay. Is everyone clear on that? Yeah, we'll definitely show the application soon. But this is the syntax. Get used to the idea of what we're doing. All right, and here's just more visual so you really understand how it works. So in this diagram, again, I've got memory. I've made up fake addresses. I've got 2. It's just a normal integer. X, it's just a normal integer storing 2. Y is a normal integer storing 99. And then I've got this x pointer, which is storing the address of x. And we think of it as pointing to x. Okay, so here, this is a variable that can store an address. That's all it's doing. And we think of that it's pointing to that variable. That's how we can sort of imagine it. Okay. Now, once we've got that, I can access the variable x without directly using the variable name x. And again, you're probably thinking, who cares? Why don't we just use x? I get it, but we'll get to it soon. So we've got a dereference operator. So this is like if you've got an address, basically going to that address. So if we say x pointer is this address. If we say star x pointer is the value stored at that address. It's like star x pointer is like going to that address and getting the value 2 out. Okay, we call it dereferencing, but it's basically going to that address and getting the value out. And we call this like indirect or indirection. Okay. Does that make sense? And yeah, you don't need pointers to do the assignment. You are welcome to use them, but you don't need them. Okay. So star goes to that address and gets, to that actual location. And in this case, there's a 2 in there. We'd be printing that out. So you can also use pointers to indirectly modify variables. So x pointer, remember, is storing this address. But if we say star x pointer, it goes to that address and we're setting that to 7. Okay. So yeah, and people might be thinking, well, why couldn't we just say x equals 7? We can, but we're going to see how this is useful when we can, Well, somebody's asking, why doesn't this have to be hexadecimal? Well, X pointer is the value in here. We're not changing that. This is still containing an address. We're going to the address that this points to and changing that to 7. Okay, this still has an address in there. We haven't touched it. We're going to that address and we're storing the value 7 there. Okay. Yeah, each address can only store one variable at a time. Someone's saying, why are we using star and ampersand on the same line? This part here is declaring the pointer variable, and this star is saying this is a pointer variable, not just a normal int. This part here is saying what's the address of X, and we're initializing this variable. Okay, so unfortunately this star thing gets used a couple of times. Once in the context of us declaring the variable to say, hey, this is a pointer variable, and when we're not declaring the variable, we use it to dereference the pointer, or basically go to that address. Okay. So just to put it all together, first step in this example anyway, I've got X, which has 42, and I've got number pointer. A long name. And I know it's a pointer because it's got this star here, but that's the name of it. Right now, it's not pointing anywhere, it's uninitialized. But here, I'm giving it the address of X, so I think of it as pointing to this X variable. Okay. So I've declared it, I've initialized it, and then in the next step, I'm using it. I'm dereferencing it. I'm saying, okay, there's an address in number pointer. I want to go to that address. That's what this star means. Go to that address. When I go there, I get the value 42 out. That's what this part's doing. I add 1. Oops. That's equal to 43. And now Z will have the 43 in there. So this line here, we're dereferencing the pointer. Number pointer stores the address of X. Star number pointer means we're basically going to X, and we get the value 42 out. All right, so let's see some examples. We'll get rid of that. So this is kind of more of the same. Let's think about what we've got. We've got X. We love, and X is not a great name, by the way, but these are just examples that don't do too much. We've got X with a value of 2, and just for the example, I will make a fake address, but we'll see when we print it out and run this, it won't be that address, but let's assume for now this is an address F0. Anyway, when we go and print this, it's going to print the int that X stores is, we're just printing out X, it has a value of 2. Now on this line here, we don't really know what it's going to print because we don't really know what the address of X is. Okay? In this example, I'm pretending that it's F0, but we really don't know. When we run it, we'll see what it is. Now down here, we've got a variable called X pointer, and it is storing this address of X. We're saying to X, what's your address? And it's giving X pointer the address. And we're thinking of it as pointing to here. Now down here, remember %p means we're printing out an address. Oops. Down here, we're just printing out the value of X pointer. So if we just print out X pointer itself, it's just printing the contents. It's just printing this address. We don't really know what the address is, but my pretend address is, F0. Now the thing is, this is where people get very confused. This is this is a variable itself. So it too will live at some address. I'm just making up another one. Okay, all of our variables have addresses. But in this case, the most important address is X because we're kind of storing that in our pointer. So is everyone sort of happy up to here? Let's run it and see what we get so far. Now, the other thing is every time we run this, our variables will be stored in different locations. It's not like every time we run it, X will be stored in the exact same place. So here, yep, we've printed out X, it was 2. Now the address of X is this big long number here. 7FFD9AFBD180. So we're very lucky and privileged to just be able to call it X in our program rather than have to worry about that too much. But we can see X pointer itself stores that exact same address. So here, I'm just going to call it 7FO. I'm going to skip all of these digits in the middle just so I don't have to write them all. Right? But they have that same address. The address of X is the same as the value that X pointer is storing, which is what we'd hope for. And then we can see that this variable also has its own address that's different, right? I'm going to call that 7F90. It doesn't matter, but it's different. So that's the scenario we've got. Now, once we've got this, what happens when we start dereferencing things? Let's have a look. Okay, that will do. So here, where can I move this where it's not in the way? Okay, sorry. Now here, what we're trying to do is we're dereferencing our X pointer variable and we're printing that out. Okay. What are we going to get when we dereference that variable? I'm just going to put it here for now. And print that out. Okay, so X pointer is pointing to X. So if we say star X pointer, it's going to print out 2. So %D gives us an integer. %P is what we use if we've got an address. Okay, so here we've got a pointer. It's got the address of X. Star is dereferencing it, and we're going to that address, and this should print out the number 2. Okay, and I might just chop some of this off so we can see it. There we go. So is everybody happy why this is going to print out 2? So line 26, x pointer is a variable. It has the address of x in it. When we dereference it, it means we go to that address and it's going to print out a 2. Now down here, we're doing the same thing. We're saying star x pointer. So when we say x pointer, that's referring to this chunk of memory here. When we say star x pointer, we're going to this address. We're going to x, and we're setting that to be 99. Okay, so after we've done that, whether we print out x, well, x is now going to be 99. If we go to the address that this is storing, we're going to x, and again, we're printing out 99. Okay? All right, any questions about how that works, that dereferencing? Okay. One more example, but we'll have a break soon. But another example is this one. I'll go through it a bit more quickly. Here, again, we've got x, which has the value 3 in it, y, which has the value 7 in it. We've got x pointer, and we've given x pointer the address of x. So this variable is storing the address of x, and we can think of it as pointing to it. We've got another variable called num pointer. What is this line doing? So just to make it more concrete, imagine x is living at some address, f0. This here would be storing f0. And all we're doing is copying the contents of this into here. So we'd be just copying the value in here to here. It'd also have the address of x in there. So now we've got 2 pointers pointing to x. Okay? So here, if I just say, what's the value in x pointer, that's the address. We're copying that address into num pointer. They're both pointing to x now. All right, so now what's this going to print out? Type it in the chat. What do you think this is going to print out? Line 13. So what's happening is, I can see some answers in there, which is great. We're printing out x and y, so that's going to be 3 and 7. But here, this is star x pointer. So it's not printing out the address, it's going to the address. So its x pointer is pointing to x. Star x pointer means it goes to x, and it's going to get out the value 3. Star num pointer means it's pointing to x, it's going to x and getting out the value 3. Okay, so both of these pointers were both pointing to x. Actually, nothing's pointing to y. Yep. Okay, now on this next line, we're saying go to where num pointer is pointing. Well, num pointer is pointing to x, and set that value to 10. So num pointer is pointing to x, we go and we're setting that to 10. So now when we print everything out, what are we going to get now? Well, x will be 10, y will still be 7, x pointer is still pointing to x, so if we do star x pointer, we'll get 10, num pointer is still pointing to x, star num pointer, we also get 10. So yeah, if I wanted to print what's in the pointer, we don't put the star. So if you don't put the star, you're printing the address that it's storing. If you put the star, we're going to that address and getting the value. All right, now on line 20, what are we actually doing now? Well, we're saying, I don't want num pointer to point where it's pointing anymore. I want it to store the address of y. So I'm actually changing this. I'm changing the value inside it and saying, actually, let's give it the address of y. I'm just going to write the address of y in there. So now we're actually changing where this is pointing, and that's fine. It's a pointer. It can point basically anywhere as long as it's pointing to an int. Okay? So now it's pointing to y. Get rid of some of my scribble. Okay, we've just done this, and our pointer is pointing to y. So what's line 23 going to print out? So if we have a look, I can see that, where am I up to? Here, x is 10, y is 7, I think. Star x pointer, well, x pointer is pointing to x, so that should be a 10. Num pointer is now pointing to y, right? So that's going to be 7. Okay? So we've got stars here, so it's not printing any addresses, it's going to those addresses and getting the values out. Okay. Then we've got on line 25, we're just going to y and setting it to 99 in the regular way we like to do it, saying y equals 99. So now if I print all of this again, well, x still has the value 10. Y now has the value 99. X pointer is still pointing to x. So if we do star x pointer, we're going to x and getting the 10 out. Num pointer is still pointing to y. So if I do star num pointer, it's going to y and getting the value out. So I think we should see something like this. And you know, we can run it and see if I was right. But yeah, this one's just showing you that, yeah, pointers can change where they're pointing to. It's pointing here and it can access this. You might change it later. Okay, it's all the same principle though. And just one thing before I go on the break, this is just an example and a reminder. I made num pointer pointed, I'll just get rid of this. Originally num pointer pointed to x. We changed it to point to y, but it's not going to be allowed to point to this value here, d, because d is a double. It's going to say, no, you're an integer pointer. You can't store the address of a double. All right, just a reminder of that. Yeah, you have to sort of define what kind of address you're pointing to. If you say that you're an integer pointer, you can only hold the addresses of integers. All right, so these are the basics of pointers. There's an exercise here that you can try yourself. There's the code. You can try and work through it like we've just done and run it and see if you get the right answers. Okay? And that's the exercise. So after the break, yeah, hopefully we'll find out what the point of all of this is. And yeah, let's come back at about 5 past. All right? Okay, how's everyone's brain going? Are we ready to sort of find out why on earth we're doing all of this? I can see some people are asking about structs. Yeah, we can have pointers to structs as well. Okay. So what's the point of this? Is everyone ready to go though? I don't want you to miss it. So, all right, back to this example here. There's no pointers in this. So even if you're completely confused with pointers, have a look at this code and think about what this is going to do and what it's going to print. So I've got variables, x is 2, y is 5. So I'm expecting if I print them out, I'm going to get 2 and 5. But then I call update, and update has an x and a y. It's adding 1 to the x. It's subtracting 1 from the y. Swap is swapping the variables. And let's just talk about swap because we mightn't have seen this before. So imagine I've got the value 2 and 5 and my x has 2 and my y has 5 in it. What I can't do, and what sometimes people want to do, is say, well, x equals y and y equals x, or something like that. And it doesn't work because as soon as you say x equals y, you're overriding your value of x. Okay? So we can't do it like that. We always use this kind of thing. Now, you don't have to call the variable temp. You can call it what you like. But the trick usually is we have another variable and we can move this value, either x or y. Here we're choosing x. We're moving that into this variable. So then we can say x equals y and put this value in, but we haven't lost our value of 2. And then we can say y equals temp and put that value of 2 in there. And then, we've got this x has 5 and this y has 2 now. We've swapped them over. So this is a standard way to swap numbers or swap things. Okay, now having said all that, we've got a function that's adding 1 to x, subtracting 1 from y. We've got a function that's putting the value of x in y and the value of y in x. What's this going to print out here? And what's this going to print out here? What do we think? And let's go and run it. So we've got exactly the same thing. I've just got the code version. Let's compile it. Okay, and I do have a return, but right, I get what you're saying. Okay, now if I do this, everything's going to be 2525, right? The values in this main never ever change. And that's because when we pass things into functions, we're passing copies. So update will have its own local copies of x and y that have the values 2 and 5 in there. Swap will have its own local copies of x and y that have the values 2 and 5 in there. And, it doesn't matter. In this example, they all happen to be called x and y, but, we could use different variables in these functions. All right, so I hope everyone realizes we're going to get 2 and 5. But let's go through the underlying sort of theory of what's happening behind the scenes. So let's talk a little bit more about memory. Now, when we compile our code with GCC, it goes and turns our C code into instructions that the machine can understand and execute. And all of those instructions get stored in RAM when we're running our program. So when we are running or executing our program, we get a chunk of memory. And in that chunk of memory, one section will be that code that's actually executing. Another section will be our global variables and static variables. Now, we're saying don't use global variables. We've never really talked about static variables. So this is not a section that we're very worried about. And neither is the code really. We've then got a section called the heap. This is going to become very important after Flex Week. But for now, the most important part of the memory we get allocated when we're executing our program, the most important part is the stack. This is the thing that keeps track of all the data related to functions and function calls. So every time we call a function, that function gets a chunk of memory on the stack where it can store its local variables and where it also stores extra information about things like, you know, when I finish this function, where do I go back to? Like what gets executed when this function ends? So it keeps track of where the function returns to and lots of other things. And when your function finishes, all of the data related to that function is basically popped off or removed from the stack, because then that memory can be used for some other function that needs to run. So let's see what's happening when we run this kind of program. And yeah, I've got bad style. I've got my function in the slide above my main. Okay, apologies for that. Now, but we know that our code's always going to start in the main. The main function will get an area in the stack. We call this a frame, but it doesn't really matter. A stack frame. But it's got room for the variables, the local variables that main is going to use, and other things that we're not going to worry about. So as we run it, this is where the main is storing its data, right? These are the variables. And we're setting x to be 2, and we know that they're at some address. We're not worrying too much about the specific addresses yet. And y is equal to 5. All right, so we've got our variables, x is 2, y is 5. Now we're calling our update function. And we're passing in the values 2 and 5. And the update function happens to call these values x and y as well. But the update function has its own chunk of memory on the stack. And these x and y parameters are both storing 2 and 5, but these are not the same memory locations. These are not actually the same variables. When we're inside the update function, it's working on its x and y's, right? So as we increment x gets updated here from 2 to 3. We're decrementing y gets decremented. It was 5 and now it's 4. So update has updated its local data, which is great. But then when it returns or finishes, that data is all gone anyway, and x and y in the main still have the original values in there, right? Because we passed in copies. Now, this is hopefully something you already kind of know, but this is just showing you what's happening on the stack as well while it's happening. Okay, and the same logic when we're calling swap, it was swapping the copies around, but not the actual original values in x and y in the main. Okay, oh yeah, and when the main finishes, it doesn't need its data on the stack either, so it all gets popped off. All right, so we have talked about this before. Except for arrays, which are a special case, when we pass data into our functions, they're passed by value or copy. We can't change the original variables back inside our original function. Is there any way around this? Well, yeah, because we know that scanf can go and modify our variables. So why don't we try and pass in the addresses of our variables to the functions like we do with scanf? And then maybe our functions can go to those addresses and modify those variables. So that's what we can do. So now in our update function, we really want update to modify our x and y variables. So we pass the address of our x and y variables in. Okay? We're going to say, we're not going to give you a copy of 2 and 5. We're going to say, here's my address. Here's my address. And we're going to pass that into the function. Now, when we do that, that means the prototype of our function has to be different. If it's just int and we're passing an address in, that's not going to compile. To store addresses, we need pointers. So these inputs, we'd have to change them to be pointers. So now our function is taking in 2 addresses of integers. And once we've got pointers, well, now we need to dereference them, right? If we're going to use them properly. So if I've got x is equal to 2, y is equal to 5, and then down here, basically what I've got is a variable x. It's called x, but it's really pointing to the main's x in this case. I've got a variable y, but it's really pointing to this y in the main, right? These are both pointers now. So if I want to go to the x that lives in the main and increment it, I've got to do star x to dereference it. That gets the 2 out. 2 plus 1 is equal to 3, and I store it back in here. So I'm actually pointing to the variables in the main. I'm dereferencing the addresses and going to those variables and updating them. And I'm doing the same with y. I'm going to that variable which has 5. 5 minus 1 is 4, and I'm storing that back. Okay? And then even when that function finishes, it has the addresses of it had the addresses, it could go to those variables and change them. Okay, and again, let's see how this looks on the stack. We've got x is 2, y is 5. We're calling our update function, but instead of just passing in the values 2 and 5, we're giving the function our addresses. So this x down here is really pointing to the x in main. This pointer variable down here is pointing to the y in main. When we update them, we're going to those variables and updating them. When our function finishes, those variables have been updated. So yeah, this is really the main point of pointers, to be able to indirectly do things like this. So we're adding the integers here because star x, if I've got a pointer, star x takes me to the value it's pointing to. So that gives us the 2. If I said x equals x plus 1 in here, yeah, I'd be changing the address of I'd be changing the address that this is storing, which would break everything. Someone's asking about the heap. We haven't learnt about the heap yet. But we shouldn't just always do anything, right? Okay. Yeah, and we can do the same thing for swap. So let's go over, yeah, you can put pointers in assignment 1. Don't feel though that you have to. You're capable of writing assignment 1 without using pointers, but if you want to use pointers, you're free to use them. Okay, so now in this code, we've fixed it partially because we've fixed the update function. So let's just see what we've got before we go further. we've got a function, we've got a program, we're passing in addresses of X and Y, so update will, oh, I've got to run the correct program though. So update will at least modify. So update is doing something now, and it's changed these to 3 and 4, but swap is still passing copies of the values. So if we want to change swap, we've got to do something similar. We want to pass in the addresses of these variables so the function can modify them. But the function has to have the correct prototype, right? Pointers can store these addresses. So our parameters have to be pointers, not integers. But if X and Y are integers, you know, this code is now not going to work. It's broken. If I want to get the value out of X, I've got to dereference this. If I want to go and get the value that it's pointing to, I've got to dereference it. Otherwise, I'm just throwing around addresses. I want to get the values that those addresses are pointing to. So I've got to do something like that. Now, if you're just blindly doing it and you're just shoving things everywhere, it'll mess it up. We only want to dereference the things that are pointers. In this case, our temp variable is just a normal integer. We just use it like a normal integer. Now, once we do this, our functions are able to properly modify the variables that are living in the main, right? So update, changed it from 2 to 5 to 3 and 4, swap them around, and now we have 4, 3. Okay. But yeah, if you want to use this in the assignment and you think in some case it might make something easier for you and nicer for you, do it. If you're just thinking, I have to use these now, oh no, what am I don't understand, don't do it. Okay. Now, somebody did ask about pointers to structs. Do we want to talk about pointers to structs now or do a Kahoot to give our brain a break from pointers? Actually, pointers to structs aren't too bad. Let's do them now. Oh, somebody's saying Kahoot, Kahoot, Kahoot. All right, we've got 2 Kahoots. Let's do Kahoots. And we'll come back. All right. Now this Kahoot has a bit of 2D array and some strings. All right, so I'll give everyone a few minutes to join. Does anyone else end up walking around singing this song sometimes? It's just me. Okay, the numbers seem to have stabilized. Oh no, there's a few more coming now. I'll give you another, say, minute to join. Oh, I think, no, let's start. Okay, let's go. I'm going to click start now. Okay, excellent. So we've got 4 rows, 5 columns. We've got basically 4 times 5 elements that we can store in this array. We didn't say what type it was. Okay, very good. All right. Okay, let's have a quick look at this one. Our first index is telling us what array we're interested in. So we've got the array at index 0, 1, and 2. So we're interested in this array here. And then within that array, or this row, within that array, we're interested in index 2. So this is 0, 1, 2. Okay, so this is the value we're interested in. Okay. Does that make sense? Yeah, it's hard when you've got a ticking clock and it's laid out in that order. Okay. Oh, next. Okay, I think they're all strings now. Yay! The null terminator at the end of a string. Yes, everyone's brain after listening to pointers for over an hour. Okay. This is my motivational string. Okay, yeah, a lot of people did get it right. The string length, basically we're just counting I space CAN exclamation mark 1, 2, 3, 4, 5, 6. So the string length won't contain the null terminator, but it does contain spaces and stuff like that. So, and punctuation, everything within those quotes, but it doesn't contain that null terminator that's just part of the underlying coding. Oh, what have I just pressed? Oh, okay, good. Yeah, well, you can directly do that as well. You can directly put it into printf%d. Okay. Okay, this was a little bit tricky. This does exist and is legal. So, and maybe some people thought there was a space in there or something. There's no space in there. This is called the empty string. And here, S in this case would just be the string that just has this null terminator. It's the empty string. Now, usually you might initialize a larger string to have this empty string, and then you might modify it. You could then string concatenate things onto it or something. But this definitely is a legitimate thing. You'll see the empty string. No characters, but it has the null terminator. And what's the point of this? It can be useful. It's sometimes like initializing something to naught in a way, but for strings, to nothing. Yay, very good. Excellent. Yep, string compare. Okay, what was it? All right. Yeah, so what we're doing is, if I've got it, this is a two-dimensional array of characters or a one-dimensional array of strings. So if you think about it, this is the string at index 0, this is the string at index 1, and this just is going to print out dog. Okay. And we haven't given the dimension here, but that's okay because C can work out this first dimension and realize, well, you just want 3 strings. Okay, and the 5 is how many letters each word can have. So each word can only have 4 letters plus the null terminator. So this is the size of each individual string. This first one represents the number of strings. It's going to think, well, you gave me 3, it's size 3. This is at index 1. And when we mark your labs, we often, we are comparing things. Depending on how we mark your labs, we might be using a Linux command called diff, or we might be running code that does something to a string compare. C needs, somebody's asking, could we leave out this dimension? No, we always need this dimension specified. We can leave this one out, but we need this specified. Okay. Oh, when you get to COMP1511, you might learn to write your own auto test commands, and you'll be able to come and work for us as an admin. Yay, that was good. So what we're doing is we're going to, we're going to like the row or the word at index 2. So that takes us here. But within that, we're going to index 3, 0, 1, 2, 3, which gives us the D. Okay? Alrighty. So there are just a few to remind you of arrays of strings. I think we might have some command line argument ones now. So I don't know if anyone will remember this, but we'll see. Okay. Okay. So when we run a program like this, these are called command line arguments, and these can be entered into our main, well, everything here is called a command line argument. They can be entered into our program through the main. And we get a variable called argc, which is an integer, which tells us how many there are. But it also includes this thing here, which is, how we've run the program. So we're going to have 1, 2, 3, 4, 5 command line arguments. It just uses white space to determine where one starts and one ends. So we'd get a variable, we'd have a variable in our main called argc, like in the prototype, it would have the value 1, 2, 3, 4, 5. So don't forget it includes that. One more. Are we ready? Let's see. Yeah, double quotes if you've got spaces to make Linux pass it in as one argument. And then of course, what if you want double quotes in your string? Anyway. Yay, very good. So we get all of these given to us in basically an array of strings called argv, and it's basically like this whole thing is our array of strings, 0, 1, 2, 3, 4. So the string in here would be hello. Okay. All right, so let's see. And if you have no idea what command line arguments are, we did them yesterday. Imaginative Rooster, well done. Funny Mantis, well done. And Zesty Dragonfly, now take screenshots, get chocolates in week 7. And well done, runners up, Mighty somebody and Gleaming something else. Okay. All right. Let's get back to pointers and what we can't wait to do, which is actually very important, working with structs and pointers to structs. Your life is going to revolve around pointers to structs in, week 7, between week 7 and 10. You'll be dreaming about them. So just a reminder, we've got some kind of struct that we've designed. I've tried to make it simple with just an X and a Y. I can declare a struct variable. I get a chunk of memory for it that we know would be living at some address. And I can access the fields, or members, I should say, with dot. So p.x can go to the X member and set it to 10. p.y can set it to 9. And yes, sometimes on my slides, I don't have return at the bottom. Sorry. So hopefully everyone's clear on that with structs. How does it work when we want to do pointers to these things? Well, here I've got p, and now I've got another variable. Now this variable here, p pointer, is not a struct. It's just a variable that can store an address. So it itself is not a struct at all, but it can store the address of a struct, and it can store the address of our p struct point. So I can say to this struct, what's your address? And this is the address where the struct sort of begins, the start of the struct, and we're storing that address. So p pointer knows how to find that struct in memory. Now, if we want to access the fields, but we've got a pointer to it, it becomes a bit annoying like this, right? Because we use the star to actually go to the struct we're interested in, but then we want to go to the field that we're interested in. Now, if we don't put these brackets in, right, I've got these brackets. If we don't put the brackets in, the order of operations doesn't work out properly. We end up going to the field first and then trying to dereference our integer field. It doesn't work. We've got to stick these brackets in to make it do the dereference first, then go to the field. And this gets quite annoying to type in and to remember to do, and it's kind of yucky. But they made an alternate syntax which does exactly the same thing. So actually, if you've got a pointer to a struct, instead of using dot, you just use arrow. So anytime you've got a pointer to a struct, just use arrow instead of the dot to access the fields. Dereference is, you know, if I've got a pointer to something, let's say we've got x, just a normal variable, x pointer. If I just say x pointer, that's talking about the address that's in there. If I say star x pointer, that's dereferencing the pointer and going to that location that it points to. You know, so if I just talk about, in this example, if I just say x pointer, I'm talking about this address. If I say star x pointer, I'm talking about this value, you know, in the location that it's pointing to, which is 50. Okay, now when we've got a pointer to a struct, instead of having to use this star to dereference thing and put it in brackets and do a dot, we can just instead do exactly the same thing using this nicer notation, which is just, we've got a pointer to a struct, let's use arrow to access the data in it. Okay, so that's kind of it. Now, pointers, just like ints and all the other types except arrays, get passed by copy into their functions. So if I've got code like this, I've got the same problem we just looked at before when we were just dealing with integers. I've got a struct p that might have some data in it. When I pass that into a function, it gets a copy of it. So it'll have its own copy with the same data in there, but it's a copy. And if it just goes and updates this copy, you know, adds one onto it, it updates the local copy and it doesn't change the original struct that's back in main. Okay, so yeah, what we can do now is we can do the same thing with structs. We can pass in addresses of structs and then allow our functions to update the data inside our structs. So let's have a look at this. I'll run the code, and then after this example, I'll probably stop so our brains don't get too overloaded. Right, so let's just go over this problem again. It's the same problem we looked at before, but we're looking at with structs. When I run this, I've got my point with 10 and 9 for x and y. I'm passing that into my function, but when I print out my px and y, it's still going to be 10 and 9 because we pass structs by copy. We pass in copies of the values. So when we update like when we pass them into functions, the function has no way to go to the original struct and modify it. So to fix that, if we want our function to be able to update our struct, we'd have to pass in the address of it. Just like we've seen before, this is just a pointer example. Well, actually, we don't necessarily have to do it like that, I should say. The other way that you could do it without using pointers, and this is possibly how people are doing things in the assignment and how I did things with Mud and Bones the other day. In this case, if I've just got one struct and I want to modify data in that, another option rather than using pointers is just to return my updated struct. So let's try update 2. This update here won't work. It's got no pointers and it's void. Let's see if we said p equals update 2 and pass our struct into that. What's update 2 doing? Well, we pass in our struct p and it gets a copy of it with the 10 and the 9 in there. And we've got our copy with the 10 and the 9. Update 2, increments it. It now becomes 11 and 10, but it returns it. When it returns it, it's returning this struct. And when we're returning it, it's assigning it to p. So we're returning this value and we're copying it over and writing over the top of this with our updated values. Okay, and this is one way to approach the assignment, packaging things in structs, returning them and assigning them to make sure you can change data that isn't in an array in other parts of your program. So this second way of doing it should work. Oops. Okay, so we were able to update our struct in main by returning the updated struct from the function and overriding the original struct. And that works well if you really only kind of want to return one thing, but sometimes you might need this return value for something else, and you actually might want to pass in a pointer so you don't need to return it. No, this update here does nothing. This update on line 20 does nothing because points are passed by copy. We'll pass a copy of this point into here with 10 and 9. We update this to 11 and 10, and that's great, this local copy. When the function finishes, this is still 10 and 9, right? This is like ints, where we can't modify our int variables that are in the main in any function we pass them into. We have to use pointers or return them. Yeah, so you either have to use pointers or a return value to modify variables from inside another function. But you can only ever return one thing. So if you're trying to modify more than one thing in a function, like from the calling function, you kind of need to use pointers. Okay, so this will give you freedom to do more things from within functions to the variables, Okay, so we wrote it one way, which can solve things, but maybe if you need the return type to return something else, you might want to pass in a pointer. So let's try that. Let's fix this version here. We want our update function to modify our struct. So we're going to pass in the address of it in this version of update. That means our update has to have a pointer, right? We're passing in an address, so this parameter has to be a pointer to store that address. Okay. Then inside this update function, we're now passing in addresses. We've got pointers. If I've got a pointer to a struct, what do I use instead of the dot? I only just told you on a few slides ago once, but we use arrow. If we've got a pointer to a struct, we use arrow instead of dot. Okay, so by passing in the address, what happens is, oops, our original P up in here, we pass the address in. Down here, we've got the address or a pointer to this original point. We use the arrow notation. We go to that actual struct and we change it. We go to that actual struct and we change it. When this function finishes, it's really been changed. The other alternative down here that works in this situation, but won't always be the best option, is that we pass in a copy of the point, we update it, and then we actually return it, and then copy over this one with it. All right, so we've used two approaches here, the pointer way and the return way. But like I said, you've only got one return value. If you're using that return value to return something else, you're going to need to pass in a pointer. These names don't have to be the same at all. These could be anything. This could be called, anything, my point. And in here, you know, all of these would be called my point. It doesn't matter. The names don't matter. It's like lots of people could have the same name, but they're not the same people. But they could also have different names, right? So we could do it like this. It doesn't change it. They're completely different variables anyway. You know, this is the P that lives in the memory set aside for update 2. This is the P that lives in the memory set aside for the main. How does update 2 know to assign P to X and Y correctly? Well, actually with structs, you can do this kind of thing. I could say struct point P2 and say P2 equals P. We can't do this with arrays, but we can do this with struct. And it'll just go and put the X in the same location in the other struct and the Y in the same location in the other struct. Okay, it just copies it all across. You're going to have two equal sized chunks of memory and it puts the same things in the same locations. Yep, it's just that order. It'll put it in the same order and make like a copy of it. So we can do that with structs. Okay, all right, I think that's enough. I think we've done so much today. There's a little bit we didn't cover, but I think it's probably for the best that we don't continue with it anyway, because we're going to talk about arrays. Yeah, even my brain's fried just from talking about it for this long. And now I think there's people talking loudly outside. All right, everyone, we can all go and have a wonderful dinner or fall asleep, whatever it is we're going to do. If you found this lecture harder than usual and more confusing than usual, that's pretty standard for the first time you use pointers, okay? So it's going to take time to get on top of these. All right, so thanks everyone for coming and have a really great Flex week. Don't forget, if you are having trouble with anything, talk to your tutor. I mean, to do with this course, talk to this tutor and talk to your tutor. Go to the help sessions, go to revision sessions, let us know. We can't solve all the problems in the world, but we can support you in this course. Okay, thanks everybody. Oh yeah, linked lists will be coming up after Flex Week. Bye. Thank you.